Hi kids, welcome back to the second installment of recapping AP Physics 1 topics for AP Physics 2. This one is on forces and Newton's laws. The essential questions that this video will be addressing. Number 1, what is a force? Generically, what does that mean? And what are some of the specific forces that you usually encounter? Or at least, what are the forces you should have learned about in AP Physics 1? We'll add a bunch of forces this year over the year. 2, why is Newton's third law significant and how can it be applied to all of the specific forces? I find that that's one that is not emphasized as much in early physics classes and becomes more and more important and relevant as we go on. So in any case, if you're not 100% sure of that law, this would be a good time to brush up on that. What's a free body diagram and why is it useful? We've all drawn some free body diagrams. They don't get super complex in this class, but you should definitely be good at doing simple ones. What happens to an object if the forces acting on it are balanced, which is Newton's first law? And what happens to an object if the forces acting on it are unbalanced, which is Newton's second law? So let's start off with forces. The symbol for forces is always an F, which is convenient, but often the forces will have operators, especially that sigma operator is a big deal with forces, and subscripts to indicate what kind of force they are. I wish that the equation sheet used more subscripts. I encourage you guys to use way more subscripts, especially when you're drawing your free body diagram, because they really can help graders and teachers and anyone reading your work understand what's going on. The definition of a force is some sort of push or pull interaction between two objects. The crucial part of that is you all already probably know that forces involve pushes and pulls, but one thing that I think people don't emphasize enough is that there have to be two objects involved in every force, and that the force itself is actually the interaction between the two. Forces are vectors, just like with many of the kinematics variables. Positive and negative forces are opposite in direction, but you can decide which way is positive, which way is negative. And occasionally you need to be able to what's called resolve the vectors into components, or do addition or subtraction with the vectors. If you don't know what that means, there will be a math review posted, and I'm also happy to help at tutor time or before school, help you learn that quick math skill. The SI unit for force is the Newton, which is a capital N. A Newton is the same as a kilogram meter per second squared. And you can measure force directly using a spring scale or any other kind of scale, or something called a force probe that you probably used if you took AP Physics 1 and will use in this class as well. So this is just a list of the specific forces that were mentioned in freshman physics and also in AP Physics 1 that will be occasionally coming up again in this class. Gravity obviously is important, and I prefer it to be labeled F sub G. And the objects involved in gravitational interactions are any objects that have mass. Gravity can be big or small, and we'll be talking about that actually specifically in a minute. And it depends on mostly the mass of the objects and how far apart they are. The second force is the normal force, which is really most of the forces that you encounter in your daily life. I prefer it to be labeled F sub N, and anytime two objects are touching, we've got a normal force. So if you give a high five, that's a small amount of normal force. If you've got an elephant standing on a table, the normal force between the elephant and the table is much bigger. The third force is the electrical force, which is Fe, and this is a force between any two objects that have a property known as charge. And we're going to do a lot more with electrical force later on in the year. But in general, if you have, individual electrons, they'll have electrical force, a small amount. And we get a bigger electrical force when we have a lot more electrons and protons, like when you pull your sock out of the dryer. And it tries to stick to any other kind of clothing item. The fourth force is friction, which is F sub F, and anytime you have two objects rubbing, we've got friction. That's not a huge one in this class, but you should be familiar with it. And likewise, tension, which is F sub T, happens anytime you have two objects connected with a string. Again, that's much more important in AP Physics 1, but you should at least be aware that when you've got a string, typically I would label it F sub t just to be clear that we're talking about tension. So Newton's third law is one that's taught like in elementary school, and I think they get you to memorize something like all actions have equal and opposite reactions, which means absolutely nothing to most people, and they don't really understand what that is. To me, Newton's third law, and I think about it this way, I just think that all forces come in pairs. Because forces by definition are actually the interaction between the objects, that is a single thing, it's a single interaction. That means that each object involved is experiencing the same interaction. It's going to be the same amount of force. The only thing that's a little bit different is one object experiences the force in one direction and the other object experiences the force in the other direction. This is actually critical because without this being true, if forces weren't equal and opposite in every interaction, then conservation of energy wouldn't be true, conservation of momentum wouldn't be true, conservation of angular momentum. So all sorts of other like hard and fast principles that dictate the way the universe works are predicated on this one important idea, that forces are single interactions that are acting on two objects at the same time. We're going to do a few examples just because I think it's really critical that you guys understand this concept. So if you had two people touching fingers like that, the interaction is a normal force, so it's going to have two normal forces, one on each object. So the person on the right experiences a normal force to the right on that object, on person B, from the hand on the left, from person A. And at the same time, the person on the left experiences the same interaction, which is a normal force. They're both going to be the same kind of force because it's a single interaction on that first hand by the second hand. And you'll notice that no matter how hard you push, they both feel the same amount of that force. And the force is going to be in opposite direction. So one hand experiences a force to the right, and the other hand is going to be experiencing a force to the left. A couple more examples of scenarios where we can talk about Newton's third law. You know, if you've got two ice skaters on a pond, for some reason, people tend to think that only the person that's pushing on the other person, only person that gets pushed feels the force. But Newton's third law says that no matter who is pushing, both ice skaters feel the same amount of force. One ice skater would be pushed to the left and the other is pushed to the right. That's why they would both move off in opposite directions. An important note here, the ice skaters might not move off in the same amount of acceleration. One of them might move off in a faster velocity than the other one. And the reason that that is true is because even though the force was the same, if one of them has more mass than the other one, the acceleration will be different. So I think this is one of the reasons why people don't always understand that the forces are the same, because it doesn't look like they're the same, because all we can see is the acceleration, not the force. So in any case, you can see clearly that they're in opposite direction, because you could intuit that those two skaters will move in opposite directions, but the amount of force on each skater is the same no matter who does the pushing. Another example, an apple falling from a tree. It's really easy to see that apple being pulled towards Earth. There's a gravity pulling downwards on it from Earth, but it turns out that that interaction is between the Earth and the apple. That means the Earth is also feeling gravity, and the Earth's gravity must be in the opposite direction. So if the apple's being pulled down, the Earth is actually being pulled up. There would be another gravitational force on the Earth, same kind of interaction, right? It has to be, it's a single interaction, it's gravity, so they're both gravity, downwards on the apple, upwards on the Earth, the same amount. However, we notice a much bigger acceleration on the apple because it's so much smaller, and we'll come back to that in a little bit. Speaking of gravity, it's one of the four fundamental forces of nature, which means that we have an equation known as the universal law of gravitation that lets you calculate gravity between any two objects anywhere in the universe. If you took AP Physics 1, you probably saw this equation before. If you didn't, bear with me. I don't think it's as hard as it looks. The equation is that the force of gravity between two objects is equal to G, which is the universal gravitational constant, so that's always just that number, 6.67 times 10 to the negative 11th, you always plug in the same thing, times the mass of object 1 times the mass of object 2, divided by the radius, or the distance between the two objects, squared. So what this equation basically shows is the bigger either of the objects is, the bigger the gravitational force between them, which shouldn't be surprising to you. And the closer those objects are to each other, the bigger the gravitational force is. And the fact that that radius is squared tells you that that equation is, or that part of the equation, that variable, is actually the most important. As objects get closer to each other, gravity gets stronger very quickly. A couple things to notice about this equation. The first is that it doesn't matter which object is m1 and which object's m2. So if you're doing the force of gravity on a ball due to Earth, the ball could be m1 and Earth could be m2, or they could flip-flop, and you're going to get the same answer either way because of that commutative property of multiplication. 2 times 4 is the same as 4 times 2. And this is kind of cool because it's in agreement with Newton's third law that the force is a single interaction and it's going to be the same on both objects. It doesn't matter which object you choose to be first, you end up with the same amount of force either way because forces always come in pairs. One other cool thing to notice, which I'm not going to go into a ton of detail, but when we are interested in objects that are close to the surface of Earth, we assume that one of the objects is going to be the Earth itself. So M1, make that the Earth, and M2 will be our test object or the other object that we're interested in. In this case, the radius is going to be the distance between the object and the center of Earth, which for all intents and purposes is just the radius of Earth, which means that we can actually lump those three variables together, the big G, M1, and the R squared, because those are all constants, and we can create a new constant that is specific to objects close to the center of Earth. And that new constant is called little g, which is the same little g we saw earlier for the acceleration of objects near the surface of Earth. And it just so happens that when you plug in those three constant values, that crazy universal gravitational constant, the mass of Earth, and the radius of Earth, you do the math, you end up with -10, which is kind of a wild coincidence if you ask me. And so to save ourselves time when we're calculating the force of gravity on objects close to Earth, instead of using that huge equation, we instead just use that -10 as sort of a combination of three constants, and we rewrite the equation as shown below. We've just solved for little g. So that other equation is kind of a shortcut. It only works on Earth because that little g is specific to Earth. Drawing a free body diagram is a really important skill that you used in AP Physics 1 and also in freshman physics, and you'll be doing in this class as well. To start from the beginning, a free body diagram is a picture of an object or a system of objects that includes only the forces acting on that object or on that system. When I say system, I mean that you could draw a free body diagram of yourself with all your clothes on. You don't have to take your clothes off to draw a free body diagram. That came out a little dirty, but anyways, I think you guys get the point. The purpose of free body diagrams is to look quickly at an object and see if the forces are balanced or unbalanced, because that tells us whether or not the object is accelerating and its velocity is changing, or whether it's not. So let's go through the process of how to draw a free body diagram that'll meet all the requirements for the AP exam. Any object or system is typically represented by a box. So if you're drawing a free body diagram of an ostrich, it doesn't look like that. It looks like this. The only thing we should ever put on free body diagrams are actual forces. Not components of forces, not speed, nothing but a force. And every force that you put on there should be drawn with an arrow. And the direction of the arrow that you draw, so the arrow should always have its tail in the box and its head out of the box, and the tail has to touch the box or it doesn't count. The direction of the arrow shows which direction the force is acting, and the length shows roughly how large the force is. Everything on your free body diagram needs to be labeled. I prefer these subscripts and as descriptive of a label as you can possibly put in. So for that ostrich, I would draw an arrow upwards. I would label it Fn because it's a normal force from the ground. And then I would draw an equal length arrow downwards, touching the box, labeled Fg for a gravitational force from the Earth. And then those little hashtag tick marks across my arrows are a quick way to say that those arrows are equal in size. And that's really helpful on the AP test because it reduces the chance that a grader is going to give you a bad score for having arrows that are slightly different in size. Lots of information can be gleaned from this free body diagram, specifically because the ostrich's velocity is not changing, right? We can see that ostrich literally standing there on the ground. We know that our free body diagram is going to have balanced forces. Which means that sigma F and A are both going to be equal to 0. No acceleration and no overall sigma force, but we'll come back to that in a slide or two. Okay, so for example, if we have a different free body diagram, that last one showed balanced forces. This one is an unbalanced free body diagram of a baseball player sliding into a base. And you'll notice that I have the same two forces we had on the ostrich, although the values might be different, normal upward from the ground and gravity downwards from Earth, and they're still balanced because this person is not going to be accelerating up or down. But there is one more force, which is we have friction acting on this person from the dirt as they slide. And from this free body diagram, we see that the y-axis forces are balanced, as I mentioned a minute ago. However, in the x-axis, we have an unbalanced force, which means that sigma F in the x direction is equal to the force of friction from dirt, and the acceleration is going to be to the left, and it's going to be not equal to 0. So this object is not at a constant velocity. Velocity will be changing, as indicated by an unbalanced free body diagram. So Newton's first and second laws basically explain those last two slides, and they bring together a couple ideas. Idea number one, that the acceleration of an object is linearly related to the net or sigma force on the object, and also that it is inversely related to the mass of the object. So the bigger the force on an object, the more it accelerates, but the bigger the mass of the object, the less it accelerates. The equation for A, which you should have definitely seen before if you took AP Physics 1, and if you took freshman physics, we used this equation, but we used a different format of it, and so you might not have recognized it because we didn't talk about acceleration. But this is a really, really important equation for the AP exam. So this equation says acceleration, you can see the linear relationship with the sigma F on the top, and the inverse relationship with the m on the bottom. And if this doesn't just jump out and make a ton of sense to you right away, please come see me and I'm happy to walk through it with you a little bit more and how to use this equation, because it definitely is something that you're going to want to be comfortable with as the year moves on. So Newton's first law is one application of this equation, specifically the application in which there is no unbalanced forces. If you add up all the forces, they're going to cancel each other out, right? The up force is the same as the down force, which would mean sigma force, or the total force, would be 0. So if you plug a 0 into this equation for the force, regardless of what the mass of the object is, the acceleration is 0. So this is Newton's first law. It's called the law of inertia. It basically says that if the object has no unbalanced forces, it's going to continue moving at the constant velocity it was moving at the beginning. That may be a velocity of 0, but it may not be. And I think that this is where it's trickiest, is when you have objects moving at a constant speed. You need to realize that constant speed means acceleration is 0, means that all the forces on the object have to be balanced. Newton's second law says that if the forces are unbalanced, then the acceleration will not be equal to 0. We will be changing velocity. So if we have any unbalanced forces on our free body diagram, the velocity is changing. Or on the flip side, if a velocity of an object is changing, there must be unbalanced forces acting on the object. And you can use the equation above to calculate any of those variables, given the other two. So if you know the sigma force, if you got your free body diagram, you can add up the values on the free body diagram to come up with your total sigma force, and you know the mass of the object. That allows you to calculate acceleration, which in turn you can use with those kinematics equations from the last slideshow to figure out where and when the object is going to be reaching a location, or what the final speed is, or all sorts of other things. All right, so that was forces and Newton's laws as quickly and efficiently as I could teach it. But I would definitely take a little bit of time to pause the video and revisit all those essential questions, taking specific notes on things you don't understand or things that were unclear, and either going back and reading the OpenStax book on those topics and or coming to see me for a refresher. Thanks for listening.